Assalamu alaikum everyone. So what we are going to do, we are going to do one example, 11.29 from chapter 11 basically. So this example is going to cover the different aspects of the frequency response, the low frequency response, the mid-band gain, and the high frequency response, and will also help you in solving the problem 3. Problem 3 of homework assignment 4. So it will help you in solving in the homework in that problem. So in the problem 3 of homework 4, you're only asked to find the low frequency response basically, because it's mentioned that you only need to find the frequency response based on those capacitance which are provided, not using the uh, transient, not the transistor capacitors or the or the parasitic capacitance. So you don't have to bring DCGS in problem 3. But here in this example, we are going to do all complete analysis. So let me start doing that one and then we can follow up. But make sure if you have any question or query, just approach to me or Dr. Wala on Thursday, so we can sort that thing, or even tomorrow with come to Dr. Wala and you can sort this one out. So we have our input, which is being applied to a source resistance RS, going to a MOS, a common source with degeneration. So we have M1 connected with a degeneration resistance known as RS1 with a value of 200 ohm. And here this is M1, RS also having value of 200 ohm. And we have a load resistance connected to VDD on the other side, RD1 having a value of 1 kilo ohm. And here we have one coupling capacitance, basically the bypass capacitance, if you remember, which we have previously seen to again alleviate the gain of a common source with degeneration, because of this degeneration resistance, the load, the gain ultimately dies down or reduces. But if we put the bypass capacitance, that bypass capacitance will be considered as short for a high frequency, and in high frequency or gain can be again enhanced. So in between the output of the first stage, we have a coupling capacitor so that we can have a separate separation between the biasing points of the two amplifiers. Previously, we have seen the coupling capacitance used between common source and source follower. But here we are seeing between two source followers. One is common source amplifiers. One is common source with degeneration, and another is purely common source. So here they are calling it a node X. It's going to a MOS M2, which is again a common source amplifier M2. And here, interestingly, between this gate and the drain, we have a resistance known as RF. And we have an output here, V out, and we have an VDD connected to RD2. Okay, so that's the circuit which is provided to us. Let me write the values. This is 1 kilo ohm, RF is 10 kilo ohm, and that's all we are given. That GM1 is equal to 8.3 millisiemens, and GM2 times RD2. So the gain is also given as 6.67. Okay. So this is the information which is provided to us, and we need to do the frequency response of the amplifier. Frequency response. Whenever it's being asked from you to do the frequency response, you need to do the overall frequency response. That should include the low frequency response and high frequency response. So frequency response in reality should be having multiple things: a low frequency response, mid-band gain, and a high frequency response. So this is the low frequency response. This part is a high frequency. This is a low frequency, and this is a mid-band gain. So if you remember, we have seen some analysis point that for the low frequency response, we need to identify the low frequency capacitance. And for the high frequency response, we have to ignore or short the low frequency capacitance and only use the transistor capacitances, or commonly called as parasitic capacitances. And for the mid-band gain, it's the same thing similar which we were doing in first 10 lectures almost, that we have to ignore both the low frequency capacitance and the high frequency capacitance. So first start with the low frequency response, and just to again clarify, in a problem 3 homework 4, you are only going to use the low frequency capacitance which are provided in your problem. You don't have to bring CJD and CJ3 just for the problem 3. Okay? For the others, you need to send, it's also mentioned. So for low frequency capacitance, what we can see and analyze, both the C1 and C2 are a low frequency capacitances. C1 is a bypass capacitance and C2 is a coupling capacitance. So let's start with the C1. We call it as related to this pole information omega L1. And interestingly, we have two low frequency capacitance, but one of them will be dominating. And which will be dominating? The one with a higher value. In this case, higher value, because this corner has to be decided. Whomever among these C1 and C2 will result into bigger value of WL, that will decide this corner, and that will be cutoff frequency. So let's start with WL1. So WL1 is pretty much straightforward. We have this node and we know the capacitance is C1. So we all are familiar with that. We have to multiply whenever we have a capacitance connected to one node and the other point is grounded, we can just multiply that capacitance with the resistance seen at this point. So resistance this point pe kya hai? We have RS1 in parallel with 1 over GM1. So we just have this one. So if I want to do the proper math and open that up, C1 RS1 times 1 over GM1, I can also make it up RS1 plus 1 over GM1. I just open the parallel thing. So this would be result into 1 plus GM1 RS1 divided by C1 times RS1. And if you see, the GM1 will be cancelled out with GM1. So this is your omega L1. So now we have all these values which are used here. We have GM1 as 8.3, milli, RS1 as 200 ohm, and C1 as 50 picofarad. So we can just plug in the values and find out the omega L1. So 1 plus 8.3 into 10 to the power minus 3 times 200 divided by 50 into 10 to the power minus 12 into 200. Okay. So if we do the math, this value will be somehow equivalent to 260. Let me just do quickly this thing. 8.3 E minus 3 into 200 plus 1 divided by 50 E minus 12 divided by 200. So this will be equal to 266 mega radians per second. Since it's an omega, it's not a hertz. If we want to interest in frequency, you need to do divide this by 2 pi. So 266 divided by 2 pi will result into around 42.4 megahertz. So we know this is FL, but we still don't know that this is the dominant or not. So for that, we need to find C2. So we'll keep this as 1 point and we'll move forward to find the impact of C2. So the C2 impact, I will redraw the circuit again to have a easy impact. But we have seen the impact of C1. Now, when we are going to find C2, impact of C2, we will short the C1 so that we can see only the impact of C2 and our analysis becomes simpler. So I will do that part. C2 RS here. Again, we know the value, so we don't have to write it at this moment. If we need, we can consult. Now, this is not common source since C1 impact is already seen. So I can safely short it. Okay, RD1. Here the coupling capacitance C2 is coming. And then here the node X. Node X is going to M2 This is M1. And here we have some capacitor resistance RF. And then we have a load RD2. And here or V out. Okay. So interestingly, we need to find the impact or the pole associated with this capacitance C2. One thing we know, this is a low frequency capacitance, low frequency pole. But the other thing, how to find it, because this capacitor is between two nodes. If we call it as V out 1 and X, so it's not like something which is connected to one node and the other terminal is grounded. And we cannot apply Miller theorem. Why? Because the Miller theorem was applied when we have some gain associated with that one. So there should be some gain in the middle where the resistor or capacitor. Here we don't even have any amplifier between out 1 and X. If I let me say this out 1, point out 1 and X. So we are not left with a Miller theorem, but what we can do, we can just try to use a small signal model. So I call the impedance seen from here, this point R int, for example, and let's draw the circuit using a small signal model. So let's draw this thing. Since we don't have VGS, so we call this as GM V in. Okay, as we don't have RS, so V in will be equal to VGS. We have here something RD1. Again, RO, let's lambda is equal to 0, so we can take RO is equal to infinite for just simplification. Then we have a capacitance C2, and then we have a resistance which is equal to R int. Okay, and this node is X. So, and what we are interested, if I call a Thevenin sort of stuff, that this is forming something like this. V Thevenin RD1, because I'm interested in finding the capacitance, the pole information. So whatever the name I give, I'm interested in this thing. What is my Vx over V Thevenin in terms of frequency? And what is the pole information? Because that will be involving this capacitance relationship. Okay? So now we know simple voltage division, Vx by V threshold will be equal to R int divided by R int plus RD1 plus 1 over SC2. And if we do this small configuration, we will end up that is equal to SC2 R int, which is basically a 0 information. And this will be equal to 1 plus R int and RD1 times SC2. And this is basically telling us the information about the pole, the second pole. So the second pole will be equal to R int plus RD1 times C2. So this is the information associated with the second pole. Sorry, just 1 over, not like this one, just 1 over. If you remember, this is equivalent to 1 plus omega by omega p something. Okay, so omega p will be inverse of this thing. So this pole information, the second pole is 1 over R internal plus RD1 times C2. Let me just make sure all of you get this thing. Omega 1, or this is 2 now, not 1, is equal to C2 times R internal plus RD1. We know the value of C2, which was given to us as 10 picofarad. We know RD1, which was given to us 1 kilo ohm, but we don't know R intrinsic or R internal. So for R internal, we can see some analogy that we have again an amplifier, which is an M2. So I'm saying A minus AV2. We have some resistance RF, which is in between these two terminals. And what we are having here, at this point, we are having a V out, and at this point we have something terminal known as Vx. So we can apply the Miller theorem and we can do something like this one. Minus AV2 resistance will come here, R1, which we are calling R int, and some resistance at the output side. Right? So we have some resistance here. We're not concerned with this resistance since there is no capacitance, but we are interested in this resistance value. And this resistance value will be applying the Miller theorem now. Instead of increasing as in the form of capacitance, here the value will be reduced by the gain amount. So it will be RF divided by 1 plus AV2. Okay, so ये आपके पास value आ जाएगी. AV2 is equal to GM to RD2, and it's given to us as 6.67 value. And RF is provided as, let me check, it's 10 kilo ohm. So the R internal comes out to be 1.5 kilo ohm approximately. Okay, so we have this one. So we can find the information about the second pole. So second pole information, omega L2 is equal to 1 over C2 R internal, whatever the name you want to give, I just give this name RD1. Now we have all information. C2 is 10 picofarad, 10 raised to minus 12. Our internal is what? We find at just 1.5 K. Let me make sure the units are consistent. 10 raised to power 3 plus RD1 is 1 10 raised to power 3. So we have something here. If we do the math, we will come out that we have 2.5 E3 times 10 E minus 12. Yeah, so we have something like this one. We have 2.5 times 10. So we have 25 and 10 to the power minus 9. So 25 E minus 9. And we have 40. I'm just doing the traditional one. So 10 to the power 9. So we have 40 megahertz, mega radians per second, which is equivalent to so the FL2 comes out to be 6.36 hertz. So this is the two things. So these are second. So if you recall the first one, FL1 was what? FL1 value was somehow around 42.4 megahertz. Also it's megahertz. So this FL1 is bigger than FL2. That's why FL1 will be the dominating one. We will use FL1 in our analysis, or not in our analysis, in the plot, that this frequency which is going to decide this low cutoff frequency will be FL1. So but we cannot reach this conclusion unless we do the math and we reach to the conclusion. Okay, so that's the way we figure it out, or solutions for our problems, especially for the low frequency response. Now coming to the homework question, since this is a homework question problem 3, it's linked with that thing. Problem 3. Yeah. So for problem 3, you have in that problem, you have ultimately 3 coupling capacitance. If I recall correctly, you have an input capacitance, C in, which is connected with some RS. You have one capacitance here. You have another capacitance. So you can easily figure it out, the relation of this configuration, and find out C in. So that somehow we have already done, and there are a couple of examples done in the book. So one impact will be because of this C in. You can call it as omega L1. Then you have an amplifier. An amplifier again, that's a source degeneration, and then you have a bypass capacitance. So bypass, I'm just giving the not the exact name, but this is going to be an omega L2. So you can also find omega L2 correspondingly. And then once you have in an output some circuit, and then you have something, for example, next to the load one, you also have another capacitance, which is C3, whatever the name, and you have some resistance which is provided to here, RO. Okay, so you have another capacitance which is going to form omega L3. So you need to do individually for C in, CB, and CL3. So C in, you already have seen in the example, we have seen CB, we just did it again now in this example, and previously also we've seen. The only concern point which comes out is going to be with the help, what's going to happen with the C3. So you don't have to worry much about the C3 point. You have to do the something similar, which we did in this example. So here, this is your V out point. Okay, and this point, whatever before an amplifier, you call it at Vx, and you need to find just V out by Vx. And that V out by Vx will have the C3 pole information. You have to get out that the pole, which does something similar, which we just did it now. And you can again use the same. If you need, you can use the common small signal model and try to do the impedances and trying to figure it out. So just give a try. It should be easy if you understand 11.29, how we figure it out, the impact of a C2. So for the small signal analysis, you can easily solve this problem, okay, for the C3. So you can easily apply this thing, but you just need to be careful how it's going to be applied. So do this thing. Now coming back to this current problem, what we are doing, we found the low frequency response, good. Now we need to find mid-band gain, ठीक है? क्योंकि हमारे पास frequency response है, mid-band gain भी आता है. For a mid-band gain, what we need, we have to ignore both the coupling capacitance, which are low frequency capacitance, and also the high frequency, which are the transistor or the your parasitic capacitance. So for that, we can simply draw the circuit without any capacitance to have an idea about the overall configuration. Okay? So I will just draw that circuit and we can have configuration. So we have again resistance. Okay. So again, when I'm finding the mid-band gain, capacitance is the small signal का bypass capacity, coupling capacitance होगी, that will be shorted. So RS, RD1. So here we have ground. So this is VDD. This node, again, no coupling capacitance. X going to the gate of M2. We have here RF. Right, so we have RF here. It's not. We have RD2 at this point, and this is the V out point for us. Okay, so we need to find the output configuration. So if we want to do a little bit analysis, we can we just saw something that this Rx is somehow, which is the input, which is the resistance, which is being seen from this point. So we can find V out by V in will be equal to Vx by V in times V out by Vx. Okay, so we can easily find these two scenarios. Okay, what will be our V out by V in? So for that, we need to find Vx by V in. So all of us know it's simple. A common source configuration. So gain is going to be minus GM1, RD1. Both of these things are given to us. And then we can find V out by Vx. So V out by Vx will be equal to minus just sorry, this is RD1, and then here the same R int will be seen at this point. So because since we are seeing at this point, so it's going to be the same R int, so RD1 in parallel with R int. So we need to be careful. ये जो हम लोगों ने दूसरा impedance देखा था, now that's coming in parallel with RD1. So we have Vx by Vin is equal to minus Gm1 RD1 parallel with R int. And V out by Vx hoga, we have already seen that was equal to minus Gm2 RD2. So or V out by V in will be ultimately non-inverting nature because two inverting are going to come. So we can write Gm1 times Gm2 times RD1 in parallel with Rn multiplied by RD2. We know the value of all of them. So if we just do a bit math, we will come out to be at 3 point somehow we previously calculated. It's going to be 25 point something. So it's equivalent to 25. So the gain for this two-stage amplifier is currently V out by V in is 25. So now we know this amplifier, this was determined by omega L1. This gain value is 25. And now we need to find this corner where it start dipping down again. Okay, so we have to find this information, which is the dominant again in the high frequency. So in the low frequency, the dominant frequency is the highest one, and in the high frequency, the dominant frequency is the lowest one. Okay, so for this analogy, we have to again see similar, which we have done in the two previous lectures, that we have to bring the parasitic or transistor capacitance. So I will draw that one and I will leave the simple analysis for you. I guess now you have did similar in the two problems you have done in the homework assignment. They were pretty much similar to what we have covered in the class. But again, make sure do with yourself. If you have any confusion, you have any concern, please come and sort out those things. Because the concepts are stronger, but at this moment still they are very much at an early state. Take a CGT1. Again, when we are doing the high frequency response, or the coupling capacitance or the bypass capacitance are going to be ignored, meaning shorted. Okay, so we are doing this thing. कोई अब आपके पास C1, C2 नहीं है. Right, so this node will be X, and this node we have RF, we have CGT2, we have, okay, so you can see we did this thing now. Here it's RF, here this is CGD2, and here we have CGS2, and CSB is in any case 0, and this known as V out, and here we have some capacitance known as CTB2. For simplification, I can draw another version of this one so you can get an idea how the configurations are going to be look like. So the VDD will be AC ground in this analysis. So we have V in RS. So I am going to write the capacitance at the nodes, which are ultimately CGS1. So we all know that this is going to be combined with something which is 1 plus AV1 times CGD1. ठीक है, हम सब कब AV1 पता है, but still I will see how we can figure it out this one. So this is going to the gate, this is here, and the CDB at this node will be equivalent to CDB1 plus 1 plus 1 over AV1 times CGT1. ठीक है, तो ये अब आपके पास यहाँ से AC ground हो गया. ठीक है, let's call it AC ground. And this node जो यहाँ से जा रहा था, which is an X node, that is ultimately going here. I will just add the other capacitance. I didn't add intentionally. because there'll be some more capacitance which are going to be added at this junction. So if we just want to talk about this node will be feeding to the RF node, but this RF will also be now considered as a R internal. So we need to see how we can do this R internal before proceeding. So so we need to see what as the capacitance. If we see this point, CGD2 will also come here and CGS2. So let's first write CGS2 plus CGD2 will also come. That will be 1 plus AV2 times CGD2. ठीक है, ये हमारे पास आ जाएंगी, and on top of it there will be resistance. That will be somehow क्या होगा, RD1 जो आपके पास rather इसको एक ही कर देते हैं, but I'm just combining these two so we can keep this for the same X point. RD1 ये AC ground है, RD1 in parallel with RN. तो ये overall ये आपके पास capacitance हो जाएगी, and this is the impedance seen at this point, and this is going to fed to the another capacitance, another MOS M2. और M2 के साथ क्या होगा, we have a V out here, we have RD2 here, and at this point we will have something which is going to be CDB2, and then we have another capacitance which will be 1 plus 1 over AV2 CGD2. So we have this one. हम दोनों का summation ultimately आ जाएगा. So we can find one pole information because of this capacitance, one pole from this capacitance, and one pole from this capacitance. So if you want, you can put the values and you can figure it out which one is the dominant. Again, the dominant one will be which one is the less. So जो भी less होगा, अगर इस किस्म की configuration आ जाती है, this means then omega P1 is the dominant. जो भी lower value आएगी, that will be the dominant, and that will be deciding the cutoff frequency. ठीक है? So I guess that's all. What we will do, will also solve the previous exam, midterm exam, and we'll upload that one. That will be considered as the next lecture, but consider this as some problem solving tricks. The only rule of thumb is that you need to make your hand dirty. You need to go into it. You need to solve the thing. If you just see the lecture and don't solve yourself, it's not going to help you. If you only make your hand dirty, you get to know, you stuck, and then you figure it out what's the solution, that will only help you in solving these stuff. Things are basic, but again, the basic concept, the fundamentals are applied again and again and again. So you make sure you sharpen those skills and apply into the problems. Now, the more you will adopt to these problem solving techniques, tricks, you will be more accustomed, or you will get a little better from this course. Okay, so that's all, and best of luck for your exam.